So I'm going to let this video play and just keep in mind to watch out for those things. What you'll see is the flash of light, the action potential moving from left to right. Okay, there's the sodium goes in. Okay, and you hopefully watch the positive character build up. Okay, it's positive over here, but it's still negative over here. That's because the action potential hasn't reached the right side over here. But what you'll hopefully see is the negative charge is going to switch to positive as we go from left to right, and that's going to cause each of these sequential voltage-gated sodium channels to open. So let's watch. Okay, there's the flash of light. It's still pretty fast. Sodium's moving through. Sodium's moving through. And remember, it's that buildup of positive charge that causes the voltage-gated sodium channels to open. Now here is a piece of terminology. The actual buildup of positive charge inside the cell when sodium rushes into the cell, that's called depolarization. A depolarization of a membrane is always when you make the inside of the cell more positive. Again, I'll repeat that. A depolarization is any time you make the inside of the cell more positive. Every time one of these green channels opens, that's a depolarization. And the depolarizations are propagated down the axon. See how the inside of the cell is getting more positive. Consequently, also the outside is getting more negative. So now we have all the sodium ions inside the cell. But that positive buildup, the positive charge buildup, is now going to cause the potassium channels to open. And they open sequentially from left to right, but remember, potassium channels opening lag behind the action potential. Again, let's watch the whole thing again just to make sure we understand it. All right? We're going to see that flash of light. That's the action potential. It moves left to right. The action potential is literally propagated. It is the movement of sodium ions in, the depolarization, the change of the inside of the cell to positive character. Okay? And then these channels close. But that positive charge buildup then causes the potassium channels to open, and potassium effluxes out. Okay, and that happens again from left to right sequentially. And one important implication of the action potential is each individual ion, one ion, say this ion right here, it doesn't have to move very far. It just has to go inside the cell through that channel. So because every individual ion doesn't have to move very far, that's what allows the action potential to spread so fast down the axon. These things occur in milliseconds, small fractions of a second, and it's because the ions don't have to move very far. Okay? Now the action potential is going to move down the axon, and it's going to go to the end called the axon terminal. The axon terminal is simply a part of the axon that synapses or forms a loose connection with another entity, either a muscle cell or another neuron usually. And the space between them, because it's not a physical connection, the space is called a synapse or a synaptic cleft. And we won't go into this in much detail here, but the action potential causes vesicles containing some neurotransmitter to be exocytosed into the synapse. And those neurotransmitters then bind to a particular neurotransmitter receptor on a receptor site, which tends to open an ion channel. One more thing I do want to take a look at is this graph up here. This is a graph that you typically see in your textbook that describes the change in voltage on the inside of the cell. So down here is more negative, and up here it's very positive. So at rest, the resting potential, the resting membrane potential, is approximately negative 70 millivolts. We hopefully know by now the initial step is the depolarization, opening of voltage-gated sodium channels and the movement of sodium into the cell. Notice when sodium comes in, we're initially going to go up in voltage on this graph, up to this peak up here, which is usually, depending on the cell, about positive 30 or positive 40 millivolts. So we had a very massive change in membrane potential. Down here it's about negative 70, and we go up to approximately positive 30 or positive 40. That phase is called the depolarization. And the depolarization literally is the influx of sodium ions, the influx of positive charge into the cell. The influx of positive charge makes the voltage more positive. So that's why it goes up in millivolts up to this peak. That's the depolarization phase. What we'll also see is the repolarization phase. All right. The repolarization phase is caused by these potassium channels opening, as we talked about. They also have a voltage sensor, which senses positive buildup on the inside. They open and potassium efflux is moving positive charge out of the cell. So if the inside is losing positive charge, then it becomes more negative, and that's why we see the graph go back down approximately to the resting level. Now, resting membrane potential is about -70. It turns out that when potassium channels are open, the membrane potential doesn't go from +30 back to -70. It actually overshoots -70 a little bit. You can hopefully see this trough down here is very low. Okay, it's lower than -70, usually about -75 millivolts. In fact, one thing we can talk about is the process of going from up here about +30 or +40 millivolts down to -70. That's the repolarization. It's essentially just reversing the depolarization. But since we overshoot -70 most of the time and get to about -75, for a brief moment we're going to be in hyperpolarization, which may or may not be shown here, and it's not. But hyperpolarization is just an extension of repolarization in which we overshoot the resting membrane value, which is -70. And then the restoration back to resting membrane potential is again caused by this sodium-potassium pump that is shown right here. All right? And that's going to bring the sodium ions back onto the outside of the cell where we want them, and that's going to bring the potassium ions back on the inside of the cell where we want them. And the reason that's going to be so important is because if we kept all the sodium ions inside the cell and the potassium ions outside and didn't pump them back where they needed to be, then we couldn't do an action potential. The action potential literally is absolutely dependent on sodium being higher outside the cell and potassium being higher inside of the cell. All right? So hopefully this video made sense. Make sure to like this video and subscribe to the channel for future videos and notifications. Thank you.